So now we've covered the two different types of covalent substances, and we've covered all the intermolecular forces, so we can have a look at the full properties of everything now and explain it. So the covalent network solids, if you've got a solid in front of you, it's just must be all completely linked up with covalent bonds. The majority of what we're going to deal with are simple covalent molecules, and so the only thing really affecting those guys are the intermolecular forces. And so we're moving on to the first one is boiling point trends. And so what you're going to have to do is you're going to have to analyze the differences between them all and work out what their intermolecular forces are. And the ones with the stronger ones will have the higher melting boiling points. And so just be aware if you're trying to explain something that why does it have a higher melting boiling point? Well, that one has stronger intermolecular forces, which are needed to break away from each other. And so that will allow them to go into the next phase. And don't forget to say there are London dispersion forces always present. So London dispersion forces for everything. This is, you're going to have to draw the Lewis dot structures for these to be able to see these things. So that one's got H bonding as well. That one is hydrogen bound to an N, O, or F. And so that one's got hydrogen bonding also. This one here is hydrogen bound to an N, O, or F again. And so that one looks like this. And so that one's, all three got hydrogen bonding. This one only has London dispersion forces, and that's very negative. Only London dispersion forces, no dipole. And so if you look at these ones, so we've got nitrogen, fluorine, and oxygen. If you look over here, the nitrogen is going to be least polar, and then you've got the oxygen and the fluorine here. But the problem is you're comparing hydrogen and fluorine with these two. So that's an interesting, difficult one because the fluorine is actually more polar. But this one here has two groups here. And so that can interlink quite well. Whereas these things, it doesn't interlink quite as well because they start interfering with each other. So it doesn't form a nice structure. Three-dimensional structure as these ones can, and so the water forms can interlink three-dimensionally a lot better than this, even though this one is actually more polar. Okay, so there's always a little bit more complexity to it. So it would be extremely mean. Again, I don't see questions. I've never seen a question with these two because normally, as you'll see with the examples coming up a bit later, it's usually just a black and white question. And in reality, there's a lot more complexity than just looking at the hydrogen bonding. There's all sorts of other things that we can go into in detail about that interrupt just that one single factor. Okay, but you just need to know that one single factor. So here are the typical questions that you're going to get. And why are they easy? Well, you stop it now and go through all of them and tell me which one's got the high melting boiling point. And I'll assume right now that you've done that. So the electronegativities are over here if you didn't realize. So this one here, the only difference is this one's more electronegative than this one. And so this one's also hydrogen bonding. And this one is just dipole-dipole. So it's this one. So normally they're just black and white. Again, this one's the hydrogen, this one's the dipole-dipole, this one's the hydrogen, this is the dipole-dipole. These are the typical questions. This one's dipole-dipole, this one's hydrogen. Don't forget, you'll get the question wrong if you don't also say it's London dispersion hydrogen, London dispersion dipole-dipole. Don't forget that. This one is just London dispersion plus dipole-dipole. Whatever, London dispersion plus hydrogen bonding. Can you see how they're quite easy? Why don't they throw something in like water? All right, so they're the sort of questions you don't get. So ethanol is like 70 degrees. I'll try and do an experiment on that. I'll throw it in the experiment section in the website. And when you get to organic, it even gets more complicated than that. There's heaps of other factors. And so these ones are both London dispersion hydrogen bonding. As I said before, this has got a longer chain. And so these things, the density of the hydrogen bonding is actually greater here. So this one's got 100 degrees Celsius boiling point. This one's only 78, I think it is. And so, they generally don't ask for you to go in depth and analyze the true complexity of it for things that don't necessarily make sense. Okay? But it's good for you to do that in class, and then they might pop up. I don't know. Okay? So let's look at some other factors here. So vapor pressure, it has to have enough kinetic energy to break free of the interactions they have between themselves. And so the stronger the intermolecular forces between the molecules, usually of the same type, it's all the same thing. The higher the intermolecular forces between them, the lower the less likely it is in going to the vapor stage. So if it has a weak IMF, it'll be more volatile, which means it'll vaporize a lot easier. So it'll either boil easier or evaporate easier. So we went to those two, difference between those two in atomic theory. And solubility as well. So if it's going to be soluble, so I'm assuming these are gases here. And so if the gases are going into here, there's two things it needs to be. It either needs to be, it's like dissolves like. So water is usually the solvent we're talking about. So it either has to be small size, or a charge, or both. So if it's something like ammonium, which is small and polar, it's extremely soluble. Same with ethanol. But even things that are non-polar, like oxygen and nitrogen, because they're small, they'll still dissolve. And even if things are enormous, like a protein, because it's polar, it's got positive ends, it's enormous, it will dissolve as well. So it either has to be polar or small, and it will still dissolve. If it's both, it's highly, highly soluble. Okay. The gases generally are non-polar. So that's just London dispersion, London dispersion, London dispersion, London dispersion, London dispersion. None of them have anything else. So if they were polar, because they like to be gases, and they don't have the polar attraction, heating them up actually decreases their solubility. So we've done solubility, we've done properties of ionic compounds. So increasing the temperature increases the solubility for ionic, but it actually decreases the solubility for the simple covalent molecules. And there's exceptions to every rule as well, but we're not going to give you nasty stuff.